Good afternoon, everyone. Let's get started. Today, we are going to talk about heaps. First, course logistics. Homework 7 will be out today, and due will be on May 16th. And this is class feedback. Half and half students prefer different types of class formats. Half of you preferred online live lecture, and about half of you preferred independent study and QA sessions. And because if I just run online lectures, then students can do independent study by themselves. So I decided to do online live lectures again. And regarding the level of lectures, students think that the current lecture level is the average or somewhat challenging. And the speed of the lectures is okay for most of you. That was class feedback. By the way, if you have any suggestions to improve this lecture, please let me know whenever you have those ideas. Okay, from now on, we are going to talk about heaps. In the last lectures, we stated we would like to build efficient sets and dictionaries, because we could solve numerous problems with dictionaries. And we set a goal to make find, insert, delete, find mean, and find max operations O log n. And we saw how we can make these three operations O log n in the last lectures. And in this lecture, we're going to make the rest of these two methods O log n. And we are going to use tree-like data structures to achieve this goal. And what is a binary heap? In this class, we're going to talk about binary heap. And a binary heap implements a priority queue, ADT. So priority queue is the concept, and a binary heap is what we actually implement, the priority queue, ADT. And we need to talk about what a priority queue or a binary heap is. They are similar to queue or stack, meaning they are just a collection of elements. However, each element, as the name suggests, this priority suggests, each element additionally has a priority. And an element with high priority is served before an element with low priority. Therefore, in the naive queues or stacks, the order of inserting the items determine the priority. However, in the case of priority queue, the priority is determined in a different way. So these are the properties of priority queue. And a binary heap is a special type of binary tree. In the last lecture, we talked about binary trees. And a binary heap is a special type of binary trees. So what is a binary heap? In the case of binary heap, which is a special type of binary tree, the value of each node must be no greater than the value of its child. So if a node's value is no greater than its child, then we call it min heap. Whereas when the node's value is less than the value of its child, we call it max heap. And I'm going to describe this property with pictures in the following slides. So don't worry about this statement if you don't understand this perfectly. And we call this property as heap order. You need to keep this term in mind. So please memorize this term, heap order. So this is the picture. In the case of min heap, as I told you, the node the value of this node is no greater than the values of its children. So 2 and 3 are greater than 1. And 2 is smaller than its children, 4 and 5. So this is what we call min heap. And in the case of max heap, the order is reversal. So the value of the node is greater than the values of its children. So 8 and 7. So 9 is greater than 8 and 7. So it's quite easy to understand with pictures. And we need to define heap ADT before we start to implement heap. The functionality of a heap is, of course, we need to be able to construct or create a new heap. And this is very important. This is the subject of today's class. We want to make find mean operation, which returns the smallest element, and delete mean, which removes the smallest element from the set and returns it. And insert item inserts a new element into the set. So heap is a collection of items, and we are going to make this find mean operation O log n. And we're going to support len operation, which returns the current size, the number of elements of the set. And before we start to implement heap, I'm going to describe how we are going to implement find mean operation. So for binary trees, from this slide, we're going to talk about min heap. Max heap is quite similar to what min heap. So when I just describe min heap, you are going to be able to implement max heap on your own. So from now on, I'm going to focus on min heap. In the case of min heap, the smallest element must be in the root node. I told you that heap is a special type of binary trees, and we are going to place the smallest element at the root node. Therefore, the find min operation is very easy. So we are going to just return the element from the root. Then it is going to be the minimum element, the smallest element in the heap. So implementing find min operation is quite easy if you just keep this property. And insert item is somewhat complicated because we need to maintain that the tree is complete. And what does it mean by complete? A complete binary tree is a binary tree in which every level, except possibly the last, is completely filled, and all the nodes are as far left as possible. I'm going to show you a picture and describe what this property complete means. So if the lowest level is not yet full, we need to add the next open position on this level. If the lowest level is full, we need to add a new node at the leftmost position on the next level. So this is the picture. We say this tree is complete because we do not have other levels unless this third level is full. So in this case, when we want to add a new item, we are going to place that new item at this position, not here, not as a child of 8 or 7 or 9, but the only place a new item can go is this place as a child of 4 to make this tree complete. And if this lowest level is full, there is no more place we can place new items. Then we are going to add a new level, the fourth level. And we are going to place new items from the leftmost position here. So this is the next place where a new item can come. And the next item will be the right child of the node 8 here. All right. So that is what a complete means and how we are going to insert new items. And because we need to maintain the heap order property, we need to, we are going to have the edit element bubble up the tree until the heap order property is satisfied. To do so, we are going to compare the new element x with its parent. If x is less than its parent, then we are going to exchange x with its parents. Then we are going to repeat this procedure with x and its new parent. So this is an example. So in this case, the heap order property is satisfied. So what was the heap order property? The parent node is smaller than its children. So 4 and 5 are larger than 3. And this heap order property is satisfied throughout all the nodes. So in this case, its children are larger than this node. 8 and 7 are larger than 5. So we are going to keep this heap order property even when we add new items. So let's say we want to add 2 here. Then what we are going to do first is just add this new item at this position. And we're going to make this node bubble up until the heap order is regained. So we compare 4 and 2, and 2 is smaller than 4. So we're going to swap these two values. So like this. And at the next level, which is the second level here, we're going to compare 2 with its parent 3 again. And because 2 is smaller than 3, we're going to swap these two values. Then 2 will be a new parent. So this is how we are going to maintain the heap order property when we insert new item. And because before we add this new node 2, the heap order property was satisfied throughout all the nodes. And if we just make sure that the new item makes the heap order property, keep the heap order property, then all the other nodes will follow the heap order property. So we don't have to worry about other nodes. We only need to care about this new node. And this is a picture. When we add 70, we just swap until it finds the right position. So because 70 is smaller than 120, it goes up. And because it's smaller than 80, it goes up again. However, it is larger than 10, it just stays there. So we're just repeating this procedure until we find the right place for the new item. So that is what insert is about. And how can it delete the mean? Because the mean value is at the root, we're just going to remove the node or the value at the root node. And we're going to fill the hole because we remove the value at the root. It's going to be a hole because there is no value. And we're going to fill the hole with the last entry in the tree. And we are going to bubble X down the heap. So in the case of inserting new item, we are bubbling up this new item to find the right place. However, in the case of deleting mean, we're going to delete the value at the root, and that is going to create a hole at the root. And we're going to fill the hole with the last entry in the tree. And we're going to bubble down the X value to maintain the heap property. And if X has a child that is smaller, then we're going to swap X with the child having the smaller element. And compare X with its new children. If X still violates the heap order property, then we're going to repeat this process again and again. I'm going to show you a picture. So in this case, if you want to delete mean, then the mean value is at the root position. So we're going to just delete this value and it's going to create a hole. And we're going to replace this hole with the last entry. The last entry is at the last level and the rightmost value. So let me say again. The last entry of the complete tree is at the rightmost node at the last level. So this one is at the last level on the rightmost side. So this is going to be the last element that goes to the root, like this. And we're going to compare this value with its two children. And because 4 is smaller than 6, we're going to replace 4 and 6, and 4 goes up. So we are bubbling down 6. So we compare these three values, and because 4 is smaller than 6, 6 goes down, bubble down. And we compare again, 6 and 5, because there is no right child, we are not going to compare this value, but these two values. And because 6 is larger than 5, it goes down once again. And after that, the heap order property is satisfied. So in this way, we're going to delete the mean value from a heap. So from now on, we are going to implement a binary heap. But up to this point, do you have any questions? All right, no questions. Okay, let's implement priority queue together. First of all, we are going to talk about how we can implement a priority queue using simple Python list. So in this class, we are implementing priority queues. First, we're going to use simple Python list, and then we're going to make develop this Python list so that our priority queue will have O log n computation. First of all, let's define priority queue. Priority queue. And we're going to implement the constructor first. And we're going to maintain a list, and we're going to store all the elements inside this list. And I told you that we need to implement this insert method where we can insert new item. We're just going to append this new item to our internal list. That's what we are going to do. And we need to implement find mean. We're going to return just mean value from this list. Okay, it's very simple. However, you need to be cautious about this. Our goal was to make this operation log n, and is the number of items inside this heap. However, it takes O n rather than O log n. And we're going to make this operation O log n towards the end of this class. In another method we need to implement is delete mean. We're going to first find the mean value and its position. That's what we first need to do. Then delete the mean value. This is what we need to do. And this is our first PPP exercise. Please send me a PPP message before you try to implement this method, and take some time and try to implement this method. All right, I'll give you 30 more seconds. Okay, thank you for sharing your answers. Let's implement this method together. I guess there are basically two approaches, and some of you came up with similar approaches. The first approach is we are going to just find the mean value first using the find mean method we implemented. And then we are going to find the mean index using the Python default method, meanval, like this. And then we are going to pop the value at mean index. And we're going to return a mean value. So this is one solution. And the thing is, it takes two for loops, one for loop and the second for loop. So it is going to be something like O2n. And another way we can improve this solution, although it's going to be same O log n, what we are going to do is first define two values. The index I and x is going to be the value of the first element. And what we are going to do is iterate through all the values inside this data and we find the mean value. If this value j is smaller than x, then we're going to replace the minimum value x with this new value at position j, and we're going to change j with I. And after this one for loop, we're going to pop the value at I, and we're going to return the minimum value x like this. So it takes just one for loop because this takes O1 because we know if we know the position, we can use rem, so it does not take more than O1 operation. So both are okay. And some students came up with one-line solution, like this. This is also okay. So any questions regarding this method? Okay, let's move on. We are going to use from now, so we use simple Python list to implement a priority queue. And what we are going to do from now on is we're going to use sorted Python list to make this simple Python list a little better. So that's what we're going to do from now on. So basically the constructor is the same. We're going to just copy this code. And when we are inserting a new item, we are going to do somewhat different things. So what we are going to do is we are going to attach the smallest value at the end of the list. So what we are going to do is smallest value, smallest item to the end of the list. So this is what we are going to do. So what we are going to do is we search through the items inside this data list. And if this value is smaller than this value at position I, we're going to increment I one by one. So we find the right place for this new item X, and we're going to insert this new item at position I. So that's what we're going to do. In this way, when we're doing inserting operation, the items inside this internal list are sorted. And once we do this, find min operation becomes very, very efficient because we just need to return the item at the end. So it's going to be 01. However, insert takes more time. And delete min becomes also very efficient because we just need to pop the last element. So in this way, by sacrificing the insert operation, you can make find min and find and delete min operations very efficient. So this is one way of making priority queue somewhat more efficient. However, what we want to do is make all these operations O log n. So sometimes it takes O(n), and the average time complexity could become O(n) rather than O log n or O1. So to make all the operations O log n, we're going to use binary heap. Another thing is if insert operation is very rare, and if we use find min and delete min operations much more than this insert operation, then we can follow this implementation. However, if we use all these three operations quite a lot, then we better use binary heap because all the operations take O log n. And to implement binary tree, I told you that it is a special type of binary trees. And there are two ways to implement binary trees. The first one was linked list using nodes. And another way is using arrays. However, we are going to use arrays in this case because the binary tree we are using is complete. What I mean by this is, let's say we have tree at this position like this, and we have children like this, second position, and third position like this. So this is complete. However, if we can add new items like this, then we better use linked list because the binary tree can have arbitrary shape. However, we are not going to deal with these types of arbitrary shapes of binary trees, but rather we are using complete binary trees. So we are going to use arrays because the implementation becomes very, very simple. So what I mean by this is, in the case of binary trees, complete binary trees, there cannot be any items like this. However, we first need to fill the third level before we can add new items at the fourth level. So when this happens, one cool thing is, I'll show you what this is. So let's have a look at the indices of these nodes. So when the trees are complete, if the parent, the index of the parent is P, then the left child will have the index 2 times P. And the right child will have the index of 2 times P plus 1. So as you can see here, if we want to know the position of each child, the left child, then we just need to multiply 2 to this position. Then it's going to be the index of the left child. And if you add 1, then it's going to be the right child. And in this case, you can do the same thing. Like multiply 2 to 3, then it's going to be the index of the left child. And this is this makes the implementation of a binary tree very, very efficient and easy. And we can find parent from children. So let's say if a child's index is Q, then its parent will have the index of Q divided by integer 2. So if you just divide 7 by 2 using integer division, then it's going to be 3, because we are just deserting the remainder, then it's going to be 3. So we can find the indices of children and the parent very easily if the tree is complete. So we're going to use arrays rather than linked lists to implement binary trees. So this is what we're going to do. So let's implement priority queue using arrays. We are going to define the default capacity of binary tree as 100. Then what we are going to do is first we need to define the constructor. We're going to place none inside this list times priority queue default capacity. And we're going to keep track of the size, because at first we do not have any items, so the size is 0. And now we can support the land method. We're just going to return self.size. That's what we can do. And we're going to implement find min operation that is going to be just return the element at the root. By the way, in the case of array-based binary trees, we are not using the index 0, because if you just start to place elements at the position 1, then implementation becomes easier. So we are not going to use the index 0. However, we are going to use from index 1. So the minimum value is going to be at 1, position 1. And we're going to implement the insert method. As I told you in the class slides, what we are going to do is because we need to maintain the heap order property, we are going to place a new element at the last place here and bubble up until it finds the right place. So that's what we are going to do. How are we going to do that? We first need to check whether we can add new element. So if you add one more element, and if it becomes the length of the list, that means we cannot add new items. In that case, we're going to double the size of our list. So this is what we discussed before midterm, like this. And what we are going to do is increment the size by 1. And we're going to find the whole. And this place is going to be a whole. So before we insert any new items, this one is whole. And if this value is smaller than the parent, then this whole is filled by its parent. So 4 goes here, and this place becomes whole. So that is the concept. So rather than placing 2 actually at this position, we are not putting 2 here unless it is the right place for 2 to come here. So we are going to keep this place as a whole, and we're going to fill this hole with the correct value. So this position is first whole, and what we are going to do is bubble up. So while this x value is smaller than its parent, because I told you that we can just find the index of parent by dividing this index using 2. The parent's index is going to be whole divided by 2. So this is going to be parent's index. And if this value is larger than x, then x needs to go up. So we're going to place the value of its parent to this whole, like this. And we're going to divide the whole, and we are inspecting the next value. So after we run through this while loop, whole is going to be the correct place for this new item x. So this is how we implement insert method. So now you might be able to understand why we are using arrays rather than linked list to implement binary heap. And if you use binary heaps, this bubbling up process is going to be very, very complicated. However, because we are using arrays, this operation becomes very easy to implement. Okay, the next method we are going to implement is delete mean. So in the case of delete mean, what we did was first remove this value and place the rightmost value at the last level to this position. And we're going to bubble down. But before we do that, we need to find the small value among its children. So that's what we are going to do. So the mean item is returned by this find mean method. And we're going to place the last element to its root, like this. And we're going to decrease the size by 1. And we're going to bubble down starting from the position 1. And we're going to return the mean item. And we're going to implement bubble down. And bubble down, for bubble down, this parameter means we're going to bubble down the item at position I. Okay. And when you're implementing this bubble down method, you could implement smaller child. So you're going to receive two values, the index of the node you want to inspect and the value of the node. And this check inspects whether one of its child is smaller than the element's value. So this is the first thing it inspects and returns the index of the smaller child, or 0 if no child is smaller. So you can implement these two methods. So this is our PPP exercises. Please send me PPP exercises before you try to implement these two methods. And if you have any questions, you can ask now. Okay, let's implement these methods together. At the first glance, these two methods might be somewhat difficult. However, if you just refer to bubble up operation here, then you can get some hints. Anyway, let's implement this method together. First, let's tackle the bubble down method first. We first need to retrieve the value at position I, and we're going to define this position I as the whole. And we're going to find the child, the index of the child, using this small child method. And we need to pass the index we want to inspect, that is going to be whole, and the value is going to be just the value. And what we do is while child is not 0, meaning that there is a small child, then we just need to bubble down. So we are replacing the value at the whole with the value of child. So we are exchanging the values. And here, we're defining this whole as child, like this. And we find the value of child like this. So we pass the new whole and the previous value like this, and we repeat this process again and again until we find the right place for this value. And at last, this whole is going to be the correct place for this value, and we're inserting this value here. So this process is bubbling down. And to bubble down, we're defining a new method, smaller child. And how are we going to implement this smaller child? We first inspect the left child first. So that is going to be 2 times the index. And if child is smaller than or equal to the self size, then we can proceed. Otherwise, we just need to return 0 because we reached the end of the list. And if child is in the correct boundary, we need to first check whether child is not self size and the right child is smaller than the left child, like this. Sorry for that. If the right child is smaller than the left child, then what we are going to do is increment the index of child. And then we compare the value of the child and the value. If that is the case, we are going to return child. There might be other ways to implement this small child. For example, we can just retrieve the index of child and child plus 1, the left and right children, and then compare each of them with the value and return the index of the child. So that can be another way to implement this smaller child. So up to this point, do you have any questions regarding priority queue implementation using binary heaps? All right, let's move on. So up to this point, we talked about how we can implement priority queues. First, we have a look at how we can implement priority queues using simple Python list. However, this was not very fast and efficient, so we switched to sorted Python list. And it took ON for inserting However, find mean and delete mean to O1. And in the case of binary heap, all three operations became O log n. So the average time complexity is much efficient. So this is what we've discussed. And from now on, we're going to talk about the applications of binary heaps. But before we move on, I would like to mention one more thing. In fact, Python offers default heap, and you don't have to implement priority queues on your own when you're solving some problems using priority queue. So if you want to solve other problems using binary heap or priority queue, you can just import heap queue from Python. Then you can use this heap queue library to solve your own problem. So how can you use this? To use this heap queue interface, you first need to define an empty list like this. And let's say we have random ordered items like this. And when you want to insert new item to this heap, what you can do is heap queue dot heap push and pass a heap list in the item you want to push. So this corresponds to our insert method. And when you want to retrieve the mean value, then you just need to heap queue dot heap pop and pass the heap. Then it will return the mean value. Like this. So the mean value 1 is passed like this, okay? And if you already have a list of items and you don't have to run this for loop, you can use heap queue heapify and pass the list, then it is going to be heapified, and the mean value comes here. But this one looks like our binary tree using arrays like this. So it follows this implementation. So you can just use this heap queue. And I'll show you one example. Using heap queue, you can solve kth largest element using heap queue. How can you do this? One approach is first we're going to construct a max heap and add all elements into the max heap. And traversing and deleting the top element using pop or pull. And we do this for k times, or k minus 1 times. And the last item is going to be kth largest element. So this is very simple, right? You just add all elements into the max heap and delete the top element k minus 1 times, then kth largest element becomes the top element. So this is how we can solve kth largest element problem. Okay. So this is very simple. So I'll show you how we can implement this. First, we need to import heap queue. That was kth largest, but here we're going to talk about kth smallest. We receive a list of numbers. So we're going to define a heap. And for numbers in nums, we're going to heap q, heap push to this heap the numbers. And we want to find the kth minimum value. Then what we are going to do is pop items from this heap k times. And the kth mean is going to be at the top. So it's very simple to implement. Okay. So this was one way of using heap queue or priority queue. And another application is sorting. Because we have quick sort and merge sort, we do not use heap sort that much. However, sometimes you could use heap sort. And this is going to be another PPP exercise. So what we are going to do is receiving the numbers, a number of lists like this, and it's going to return the sorted list like this. So you can just use the heap queue and try to solve this heap sort. I'll give you some minutes. Before you try to solve this problem, please send me a PPP message. This one is quite easy. All right, thank you for sharing your answers. Let's solve this problem together. Actually, this one is from Sumin. We first need to define the heap like this. And what we're going to do is first insert all these items inside this nums list. Then the numbers are going to be sorted in the heap way. So we're going to push all the numbers to our heap. And what we are going to do is retrieve the minimum values until the heap is empty, heap becomes empty. So while heap is not empty, we're going to heap pop, and this operation returns the minimum value, and the sorted nums are going to retrieve the minimum values in sequence. And we're going to return the sorted nums like this. So first, we put all the values, push all the values into the heap and retrieve the minimum value step by step. And the sorted num will have numbers in a sorted manner. Do you have any questions regarding this problem? Okay, this is the end of today's lecture. If you have any questions, you can stay here. Otherwise, you can leave now. Thank you for your participation.